What we're going to do now is establish some algebraic ground rules to symmetry. All right. So far in the first video, this is a very visual concept, so we approach it very visually. But what happens when I have an equation and I want to know, right, is the graph of this equation, can I anticipate it being symmetric about the x-axis, the y-axis, the origin? How can I make those predictions? How can I determine that algebraically without actually looking at a graph, if you would, right? And it turns out that there is a way to do that, and we're going to kind of set that ground rule up. To understand what's about to happen here, let's remember what a solution point is, right? There's some equation out there, right? And the solution point basically solves this equation. We collect enough of those solution points and we end up with the graph that we see, right? So here's all the solution points to some graph. So that's imperative to understand. Don't forget what a solution point is. That's what it's all about. And since we're looking at a graph and whether it's symmetric, we're technically looking at the solutions to some equation. So what I want to kind of figure out is there a way to establish a relationship, right? What relationship exists between the solution points on a graph, right, that is symmetric about the x-axis? Can we come up with some sort of relationship? Well, before we start looking at a graph and equation, how about we just take a look at what we just previously did in the last example, right? In the last example, we had -2, 3, and we found that to be symmetric about the x-axis, we had to just visually move it down, right? Reflect it or flip it through the x-axis, right? And we got -2, -3. And if you take just a look at that one data point, right, you can imagine a graph happening here in a moment, but if you just look at that one data point, do you see what changed? What basically occurred? Right? And if you're having trouble seeing it, or if you're waiting for me to say it, it's the 3. Right? So notice both these ordered pairs have -2 as the x-coordinate, but what's different is we have the opposite for the y-coordinate, right? We're 3 up here, and we're -3 down here. So basically what happens, right, is that x, y is a solution point. Also means that x, -y is a solution point. So my x-coordinate stays the same, but my y-coordinate turns into its opposite. And that is how we end up getting something that's symmetric. So let's go look again. I think we had a graph. We completed this graph. Let me try to sketch it as the best that I can here. Right? So here's a graph, right, that we claimed or we know is symmetric about the x-axis. And so you'll notice, right, that again, no matter what ordered pair we use, like this one right here, there's the ordered pair x, y. It's on the graph, so it solves some equation that created that graph. But its mirror image is down here, and as we saw, right, the x-coordinate is the same at that data point, but the y-coordinate is now the opposite. All right, and so basically both of these have to be, right, solution points to my equation. And what this basically means is, right, in terms of a rule or a test, right, is if we can sub x, y into my equation, do some math, and basically get the same equation back, that basically will be our proof for symmetry about the x-axis. Because if we can get the same equation back, right, that means x and y is there. And keep in mind, usually our equations are, you know, something like x squared plus y squared equals 9 squared. So I have an equation that already has x and y's in it, right? So if this guy solves this equation, and this guy also solves that equation, right, if I can sub that new point in there, right, with the y equal to -y, right, if I can plug it into the equation, do some math, and get back to the original equation, I'm basically symmetric with that. So I'll put that in some role play. We'll actually use that in a moment, but it's imperative to realize, right, that xy and x -y are solution points to that. We're going to take advantage of that in our test. So what about the y-axis? Same thing, right? So is there a relationship between the solution points on the graph of equation that is symmetrical about the y-axis. So let's go back and do what we did a little earlier, right? So we basically took the point -2, 3, right? And to be symmetrical about the y-axis, we said, well, it's got to be a mirror image about that y-axis. And so we found that 2, 3 happens to be the same thing, right? And using the same thing we did up in number 3 here, when we're talking about the x-axis, take a look at the data points, right? As we move from one side of the y-axis to the other mirror image side, what seemed to change, right? What was the one thing that changed, right? And the y-axis stayed the same, but now it's the x-axis, all right? So that is what actually changed there. So our y stayed the same, x stayed different. So if we actually took a look at a graph of this situation, right, I think a classic graph would be something that is, let's say, parabolic, right? There's a nice parabolic, clearly symmetrical about the y-axis, right? Even if we use, how about I use the graph that we did in the earlier video, right? We had a graph that pretty much looked like this. So if I have a point, you know, let's call it x comma y over here, then its mirror image -x comma y has to be on the other side. So the y stays the same, but now it's the x coordinates that are changing, even over here, right? If I have an x comma y over here, then its mirror image is -x comma y there, mirror image. So again, what this is saying is that -xy and xy, right, they are both solution points. They basically solve the same equation. All right, and so in terms of coming up with a rule or an observation that we can do, right, what we're going to do is we're going to sub -xy into the equation. I'm going to do some math, and if I get the same equation, that means we are symmetric with the y-axis, because the ordered pair -xy will solve the same equation that the ordered pair xy does. So xy, again, that's how things normally look, right? We start with some equation xy. If I can mess around with the input and come back to my original equation, I must have the same solution. I have a different solution point, but it's the solution to the same equation. All right, so there's basically kind of the idea behind our test, if you would, that'll come up. So last one, right? What about the origin? Well, again, let's go ahead and take a look at what we did. Right, we had -2, 3. Right, we did a double flip or a rotation, and we end up finding that its mirror image, you know, the 180-degree turn around that was actually at 2, -3. All right, and this one, what happened here is everybody changed. Right, just notice that the x-coordinate became its opposite. Right, we went from -2 to 2, and the y-coordinate became its opposite. Right, we went from +3 to -3. So as opposed to the last two where only the y was opposite, only the x was opposite, now what we have here is that they're both opposites. And again, if you go back to the original video that we did, I think we had this function that we claimed was symmetric about the origin. And so that means this data point here, x comma y, right, if we rotate it or double flipped it, right, its mirror image around the origin would be -x, -y, or vice versa. And so basically this guy and this guy are solution points to the same equation. And so what this means in terms of an algebraic test, right, an algebraic rule, is if I sub -x, -y into the equation, do some math, right, whatever that math looks like, then if we get the same equation, that means that xy is the solution, and it means that -x, -y is also a solution because they have the same set. So we're going to put those tests into play using some examples. Hopefully, again, kind of a very abstract concept. Algebra obviously is very abstract, but hopefully gives you a good idea. So symmetry about the x-axis, we're replacing y with -y and seeing if we get the same equation back. For symmetry about the y-axis, we're replacing x with negative x and seeing if we get the same equation back. For the origin, we're replacing both of them with their negatives, right? Their opposites, if you would, and seeing if we get the same equation back. Let's put that into practice in some homework-like problems.